So in this video, we're going to introduce the concept of isomorphism. And we're going to do this in a way that has basically nothing to do with group theory for the time being. And then in the next video, we look particularly at group isomorphisms. So the thing to understand about isomorphism as a concept is that it essentially refers to the idea of relabeling something in a way that doesn't change anything about the math. So I'll give you a couple simple examples. So I'm sure that when we see this, every single person, if you're an English speaking person, you look at these and you read these out in your head as 1, 2, 3, 4, 5. On the other hand, I can think of a whole bunch of other possible representations of these numbers. How about like these guys? Or if you're a French speaking person, maybe like so. And every language ever has their own, pronunciations of these things, but under no circumstances does anything about what you call these numbers matter. The names are irrelevant. And so all of these ways of talking about numbers are, for all intents and purposes, exactly the same. And so you could think of this as your prototypical example of an isomorphism. I want to show at least two more examples that are a little bit more mathy. Next one that I have in mind is from an area of math called graph theory, which is fine if you don't know anything about. Maybe we'll label these guys as follows. Graph theory is the mathematical study of networks. And so a graph is a bunch of nodes, vertices, connected by edges, line segments. And so here is a graph, right? We have 4 vertices connected by 5 edges. On the other hand, I could also make a different graph with 4 vertices and 5 edges and label them differently. How about we go like this instead? These graphs look a little different because I've drawn them slightly differently. This one's a little bit more oblong, a little bit more slanted, and it's sort of vertically oriented. We can see this vertical segment here, while this guy's horizontally oriented. And the names of the vertices are all different. But I think you guys agree that at a glance, we can tell that these graphs are the same. For example, if I turn this one over, maybe to the right, 90 degrees, and then I relabel the vertices, then we can see that these are the same. And so a graph isomorphism is the mathematical information that we need to tell that they're the same. In other words, it's the method by which we would relabel the vertices. So maybe the way the relabeling should go is by some kind of function. It should be a function from the first graph's vertices to the second graph. I don't want to scroll down too far. I want to be able to see everything. Which shows the relabeling. So maybe the way the relabeling works is we'll call this function f, and then we can say that f of 1 is b, f of 2 is c, f of 3 is d, and f of 4 is a. And if I've done this right, you guys should probably check over my work to make sure that what I've done here is I have essentially rotated one graph onto the other so that now all the edges line up in exactly the same way. All right, one more example that I think is probably very familiar to just about all of us. This is in geometry. We have a notion of sameness. which is congruence. I forget how we typically notate congruence. Is it like this? I don't know. It's been a while. No matter how you draw the symbol, you guys agree that we know what it means for two shapes to be congruent, even when the shapes are different. So what do I mean by that? What I mean is literally different shapes. In other words, positioned differently in the plane, different orientations, can still nevertheless be congruent. So like here is a long, thin right triangle. And you will notice that the long edge is clockwise from the short edge. If I have a different long, thin triangle like this with the same dimensions, nobody criticized my dimensions here. You know, this is it's not our class, right? I say they're the same, so they're the same. That's how it works. These two things can be congruent if their dimensions are the same, even though they're positioned far away from each other and have opposite orientation. It doesn't matter. We've seen many arguments of the form this triangle is congruent to that triangle with like, I don't know, angle side angle or something, right? You know, where you argue based on some geometrical considerations that these two things are still nevertheless the same. So in essence, every self-respecting mathematical object, probably should put this on our little board, has a notion of sameness. And there's usually even more than one notion of sameness, where you can be literally equal, as in like the two triangles are exactly the same. They have the same three vertices, so they're literally on top of each other. And some more general form of sameness, where they're not equal, but everything important about them is still nevertheless the same, like their lengths and angles and so on for a triangle, or the relationship between their vertices for a graph, and so on. The next concept that we're going to investigate is what does this notion of sameness, this concept of isomorphism, how does it manifest itself specifically for groups? How can we tell which groups that we've seen are secretly the same as which other groups?